So while this course is called multivariable calculus, up to now, what we've looked at so far are just variables, are functions rather, with three variables. So f of x, y, where we're calling that z. However, we can have more than two independent variables. It's possible to have some function with 4 or 5 or 6 or infinite number of variables. So what we're going to start looking at is what happens if we have some function with three independent variables. Well, the difficulty is that it's hard to visualize them because if there's three independent variables, this is a 4-dimensional surface. So what we do, the idea, since we can't easily visualize 4-dimensional space, is we're going to graph level surfaces. So we'll set our function, equal to some constant, and we'll change these constants. We'll set it equal to a constant, and it will describe a level surface. Let me give an example of that. So let's imagine that you have some function f of x, y, z, and it equals x squared plus y squared plus z squared. Well, this is a 4-dimensional object, but what we could do is think about, when f of x, y, z equals 0, what is this shape? Well, this is a sphere with radius equals 0, so it's not really anything. And then we could let f of x, y, z equal 1, x squared plus y squared plus z squared. And here we've got a sphere where our radius equals 1. And then we could let it equal 4. Again, we've got a sphere where our radius equals 2. So what we could do is represent this 4D shape with concentric spheres, where each sphere, like exactly the same as a contour line, is now a contour shape, and that so each sphere represents a different value for my dependent variable f of x, y, z. This will take your head a little bit of time to wrap around. Luckily, we've got some good examples to help illustrate this. So what we're doing, we represent a function of three variables with a family, so a bunch of level surfaces. So no longer level curves, but level surfaces, whether it be paraboloids or spheres or parabolic cylinders. So the idea is that we could represent a function of two variables as a family of level curves, where we set our two-variable function equal to some constant for various values of the constant. Likewise, as I said before, we could set our three independent variable function to a constant for various number of constants, allowing C to vary. And what we're going to get is a family of level surfaces. Three-dimensional. So we'll get a family of three-dimensional shapes. So imagine this will look a little familiar to the problem that we just did, but the temperature depends on x, y, and z. So we've got four variables. We've got x, y, z, and temperature. And it says, what do the level surfaces of the function look like? Well, we've already looked at this. X squared plus y squared plus z squared is going to create a bunch of spheres. And as our spheres get bigger and bigger and bigger, they represent temperature increasing. And so what does that look like in terms of, because this is still two-dimensional, but here's our attempt at looking at this in a 3D model. So we've got these concentric spheres. So my first sphere, my second sphere, my third sphere, and they correspond to everything on a given sphere, on that given 3D shape corresponds to a temperature that's constant. So everywhere on that inner sphere is a temperature of 100. Anywhere on that the next sphere, temperature of 200, and anything on this outer sphere has a temperature of 300. So the idea is these shapes are constant. Anywhere on this three-dimensional shape is a constant for my dependent variable, in this case t. Okay, so looking at some more examples, we've got the three-dimensional shape x squared plus y squared. Well, even though there's only two variables in here, it's a three-variable system, which means that z can be anything. So what we get here, x squared plus y squared creates a circle. And that z is not part of the function means z can be anything. So that runs the gamut and creates this, that z is sort of independently acting. And we get these cylinders. So the idea is we can say, we set our dependent variable to some constant. So we could say 1 equals x squared plus y squared. So there we get a cylinder with radius 1, and we see it right here. And then we could say 2 equals x squared plus y squared. And now we've got a radius of root 2. And we see that in here. And so everything on these spheres, everything on these cylinders, so for example, on this outer cylinder where c equals 3, everything on this cylinder has a value of f of x, y, z equaling 3. So my dependent variable, which is a function of x, y, and z, everywhere on that three-dimensional surface, which is a cylinder, has a value of 3. Looking at this next one, I've got g of x, y, z equals z minus y. What does this look like? Well, again, we could set my dependent variable to a bunch of different values of c. So we could say like 0 equals z minus y. And if we rewrote that, we'd get z equals y. So this defines a plane, and we looked at planes in the last video. So that's this plane right here. So everywhere on this plane, has the dependent variable equals 0. And then we could let the dependent variable equal 1, and we get z minus y again. Or we could rewrite that as z equals 1 plus 1 plus y. And that's this curve here. So everything on that plane in there has a dependent variable equal to 1. So whereas before we were graphing, one three-dimensional surface, now when we've got four variables, three independent and one dependent, when you have four variables, the way that we graph this is a bunch of layering surfaces where each layer corresponds to a different value of my dependent variable. Okay, well, it's important for us to have some familiarity with different shapes. So I know one of our favorite topics in pre-cal is conics. Well, conics is fun in 2 dimensions, but it's amazing in 3 dimensions. So this is 3-dimensional conics. So I'm just going to give you a chance to look at these. Here's a hyperboloid. A hyperboloid has this general equation: x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. And if that is if it falls into this form, what we get is a shape that is symmetric around the z-axis, and it is one sheet. One sheet versus this example here of 2 sheets. And when we get 2 sheets, the equation is very similar, except instead of equaling 1, it equals -1. And if it equals 0, instead of getting a hyperboloid, what we get is a cone. So I don't want to spend too much time developing those graphs. It's exactly the same as the development in pre-cal. Rather, I just want you to have some familiarity with when you see a graph that falls into these forms to have an understanding of what that graph is going to look like. And the important thing on the topic of today is if we're talking about a 4-dimensional equation, this would be just one contour surface. And there would be many more contour surfaces. Okay, so now let's try to connect these two. The idea of a function of 2 variables and a function of 3 variables. So the idea being, let's go down to if we have a 2-variable system, f of x, y equals x squared plus y squared plus 3, we know from familiarity that this ends up being a 3-dimensional parabola that has been lifted up by 3. And what is its connection to our 4-dimensional system? G of x, y, z equals x squared plus y squared plus 3 minus z. There's certainly a huge obvious connection to these, but what is that obvious connection? Well, if we were to set g of x, y equal to 0, so we say c equals 0, we get x squared plus y squared plus 3 minus z. And if we solve that equation for z, we get z equals x squared plus y squared plus 3, which is exactly this 3D system that we were looking at before. So the connection between these two is that the top is the level surface when c equals 0. So this shape here is our level surface. So everything on that surface, anything that's on that 3D parabola, our g value, which is in terms of x, y, and z, would be 0. So the idea is this. A single surface that is the graph of a two-variable function f of x, y is exactly just one member of the family of level surfaces representing the three-variable function. Said again, if we were to have a two-variable system, z equals f of x minus y, our three or this is a three-dimension. This is 3D, three dimensions, x, y, and z. We can talk about four dimensions as g of x, y, z, and in four dimensions we think of that as f of x, y minus our z value, and this, the connection between this and this, what's the connection? Well, the graph of f of x, y is the level surface when, so it is the level surface when z equals 0. Sorry, not z, when g equals 0. Because if we set this function equal to 0, then and solve this equation for z, we'd get this back here. Okay, so this, in all honesty, takes a while to really sort of grasp the idea that a three-dimensional system creates one surface. A four-dimensional system creates a number of level surfaces, a number of 3D shapes that that are wrapped inside of each other. I like to think of this in terms of those little dolls that you sometimes see, little kids' toys. You've got like some little person. They're usually carved and nicely painted, and then you can. There's a big person inside of them that you could, or outside of them, and you can uncrack that. And then there's like another little figurine inside, and then another, sorry, figurine outside rather. So you have all these little dolls. I don't know if this is making any sense, but you have all these dolls inside of each other. So if you were to open this first one, there's another doll inside, and then open that, and then there's another doll inside. Open that. So the idea is you have all of these three-dimensional surfaces kind of connected, and those three-dimensional surfaces each are representing one of the contour values for a constant dependent variable. So each of these have a constant dependent variable. All right, well, let's just go down to a kind of a simplified problem. It says write the level surface write this level surface as the graph of a function f of x, y. So here's a level surface. Our function x, y, z equals x plus 2y plus 3z. And we're looking at all the values. We want to look at the level surface where this function equals 5. So this is a four-dimensional system, and it's a level surface where every value equals 5. But we want to think about it as a graph of just 3 dimensions, f of x, y. So the idea is, just take this equation and solve it for z. And if we do that, we get z equals 5 minus x minus 2y all over 3. And this we can consider as a function x comma y. So just, it may seem obvious, but and maybe it is obvious, but really just impressed upon the idea. We started with there's a four-dimensional system. F of x, y, z is our dependent variable. I've got 3 independent variables, x, y, and z. We're writing a level surface where my dependent variable is 5. And so to draw that level surface, we're going to draw that level surface as a 3D shape. And to do that, we took our equation and we solved it for z. And now we have a linear function. It's going to be a plane. All right, some more examples here. So find a formula of the function f of x, y, z whose level surface f equals 4 is a sphere of radius 2, centered at the origin. Well, if it's a sphere of radius 2, we know that x squared plus y squared plus z squared, the equation for a sphere, equals, well, if it has a radius 2, we want the level surface to be 4, 2 squared. This is the equation for a sphere, and it equals 4, which is what we want it to do. So find a formula for f of x, y, z whose level surface when f equals 4 is a sphere of radius 2, centered at the origin. So this is the equation for our level surface. But if we're trying to find an equation for x, y, z, the general equation for f of x, y, z would be just x squared plus y squared plus z squared. This is the general equation, and it fits our restrictions, which is that it has a level surface when our value is 4 of a sphere, x squared plus y squared plus z squared, centered at the origin. Okay, now it says write the level surface x squared plus y plus root z equals 1 as the graph of a function f of x, y. So just really hit it home. We have a function that's in terms of 3 variables. And it equals x squared plus y plus root z. And we are looking at the level surface that we're talking about is setting our dependent variable to be a constant, which equals 1. So we're saying this equals 1. And now what we want to do is write this level surface, which is just for one set constant value of my dependent variable. So we want to write this level surface as a 3-dimensional system, as a graph of f of x, y. So we're just going to solve that for z. So we get z, or root z, equals 1 minus x squared minus 1, or minus y. So z, which is f of x, y, equals 1 minus x squared minus y squared. So here is our three-dimensional equation which describes the level surface of my 4D system when my dependent variable is 1. Last example says find a formula for a function f of x, y, z whose level surfaces are spheres centered at the point A, B, C. So this is just to get the idea of an equation for a sphere, given it some transformation, so it's no longer at the origin. So our function would be x minus my x transformation, so x minus a squared plus y minus b squared plus z minus c squared. All right, so this is some pretty tricky visual material to really grasp. I encourage you to spend some time just using the 3D grapher on the Moodle site. I also encourage you to maybe go back and rewatch this again because it's once it clicks, it'll be really simple for you to understand, but it does take a little bit of a leap to get the connection between level surfaces from a 4D system and their connection to a 3D graph.